All right, we're at section 1310. We're going to be discussing interference of waves. Um, Here's the PowerPoint and my notes. You might be wondering what happens when two or more waves pass through the same region of space at the same time. Two traveling waves can meet and pass through each other without being destroyed or even altered. For instance, when two pebbles are thrown into a pond, the expanding circular waves don't destroy each other. In fact, the ripples pass through each other. In the same way, when sound waves from two sources move through air, they pass through each other. In the region of overlap, the resulting wave is found by adding the displacements of the individual waves. For such analysis, the superposition principle applies. When two or more traveling waves encounter each other while moving through a medium, the resulting wave is found by adding together the displacements of the individual waves point by point. Experiments show that the superposition principle is valid only when the individual waves have small amplitudes of displacement, which is an assumption we make in all our examples. Uh, for example, if you're listening to a band and you're hearing a trumpet over here and a saxophone over here and the drums in the back, you're not getting separate waves from each one. You're getting an addition of all the waves in the air molecules that reach your ears. So it's a superposition of all the instruments that are coming. The same as if you're in a room with multiple conversations going, you don't have a different wave coming from one person and a different wave coming from the other. They all add to make a superposition wave that you can hear. Your ear distinguishes between the different sounds. Uh, okay. Um, the two top figures show two waves of the same amplitude and frequency. Let's imagine that at some instant of time, these two waves are traveling through the same region of space. In this case, the resultant wave at that instant would be a shape like that shown in the lower figure. For example, suppose the waves are water waves of amplitude 1 meter. At the instant they overlap so that the crest meets crest and trough meets trough, the resultant wave has an amplitude of 2 meters. Waves coming together like that are said to be in phase and to exhibit constructive interference. Um, oh, wrong one. Okay, the two top figures show two similar waves. In this case, the crest of one coincides with the trough of the other. So one wave is inverted relative to the other. The resultant wave shown in the bottom figure of if these were, I'm sorry, the resultant wave shown in the bottom figure, if these were water waves coming together, one of the waves would exert an upward force on an individual drop of water. At the same instant, the other wave was exerting a downward force. The result would be no motion of the water at all. In such a situation, the two waves are said to be 180 degrees out of phase and to exhibit destructive interference. You can also take two speakers, might be able to do this in the lab, move two speakers, and when you move one a half wavelength, you'll have the same destructive interference, and you'll hear the sounds diminish as the speakers come to a half wavelength. Um, it depends on where you are in the room whether you hear it or not. Some people will hear it at different times. Okay. This figure shows constructive interference in two pulses uh, moving toward each other along a stretched string. Uh, this is constructive. They build up. Uh, and this figure shows destructive interference in two pulses. Notice in both this figure and the one on the preceding slide that when the two pulses separate, their shapes are unchanged as if they were never met. We can go back to the previous one. You can see that if you look at A and E, you can see the shape of the waves are the same. And the same in this one. Even though there's destructive interference, once they get past each other, if you compare A and E again, you'll see that they're the same. Okay. Ooh. Okay, so far we've assumed waves could travel indefinitely without striking anything. Whenever a traveling wave reaches a boundary, part or all of the wave is reflected. For example, let's consider a pulse traveling on a string that is fixed at one end, as in the figure. When the pulse reaches the wall, it is reflected. Note that the reflected pulse is inverted. Let's think about why this is the case. When the pulse meets the wall, the string exerts an upward force on the wall. According to Newton's third law, the wall must exert an equal and opposite downward reaction force on the string. This downward force causes the pulse to invert on reflection. We're all familiar with reflection of sound waves. You can hear sound waves bouncing off of buildings from. Oftentimes, I would be walking and I would hear the big C5s that fly into Kelly, and it would sound like it was coming um, from ahead of me when actually I was hearing the reflection of the sound waves coming off a building, and the plane was actually coming behind me. Kind of disconcerting when you suddenly see a plane behind you when you thought it was ahead of you. Next slide. Let's. Okay. Reflection of waves. Oh, that's the next section. Well, let's just finish it up here because I don't think it's that much. Um, Now let's imagine. So this is 1311. Now let's imagine our pulse arrives at the string's end, and the end is attached to a ring of negligible mass that is free to slide along the post without friction, as shown in the figures. Again, the pulse is reflected, but this time it is not inverted. When it reaches the post, the pulse exerts a force on the string, causing it to accelerate upward. The ring then returns to its original position by the downward position of the tension in the string. When a pulse reaches a boundary, it's partly reflected and partly transmitted past the boundary into the new medium. So you can see the incident pulse, it hits the ring goes up, and it reflects the pulse. Okay, I think that's the last slide. Um, okay, oops, that's just the summary. Stop share.